Internal energy is the term that's used to describe all of the potential and kinetic energies for a system. And this sounds like kind of a simple thing, but I'm going to ask you to consider 3 examples and then extrapolate. So to start, imagine a single hydrogen atom that's moving in space. That hydrogen atom consists of 1 proton and 1 electron, and you have a couple of different energies. You have a potential energy for the attraction between a positively charged proton and a negatively charged electron, and you have the kinetic energy of the proton moving through space and the kinetic energy of the electron moving through space. And imagining that this atom is the only thing in the entire universe, these would be the only energies associated with it. And that would be 3 different energies. Now we'll consider 2 atoms, 2 hydrogen atoms. You have several more attractions. With 2 protons and 2 electrons to deal with, you don't have a single attraction anymore. Now you have 4 separate attractions to deal with. And because you have more than 1 proton, now you have to deal with proton-proton repulsions. Remember that like charges will repel one another. You also have 2 electrons, so you have electron-electron repulsions. In addition to the potential energies, you also have the kinetic energies for each one of the particles moving in space. So you have a proton 1 moving, proton 2, electron 1, and electron 2. And this means that you have 10 separate energies that you have to account for. Our third example will be 3 hydrogen atoms. And our third example has 21 separate energies to take into account. You can see that it quickly gets unmanageable to track all of these energies. If we wanted to find the total internal energy for 3 atoms, for example, that would be a lot of work. Imagine what would happen if you had billions and billions and billions of atoms to keep track of. It quickly becomes impossible. Thankfully, it's a lot easier to track changes in internal energy than it is to calculate the absolute number. The reason that the changes in internal energy are easier to track than the actual value for internal energy is because energy is a state function. And a state function is a quantity that only depends on the initial and final conditions. It is said to be path independent. It doesn't matter how you get there. And we can translate this into a mathematical expression. We can say that the change in internal energy is delta E, and that's simply equal to the internal energy at whatever the final conditions are, minus the internal energy at whatever the initial conditions were. And in addition to mathematically, we can relate this graphically. Consider the reaction of hydrogen plus oxygen to make water and heat. You start with hydrogen and oxygen. They react, and heat is released, and you end up with water. You've moved from an initially high energy system to a low energy system. And you know that the final conditions must be lower in energy because heat was released as part of this reaction. Remember that the change in energy is equal to the final energy minus the initial energy. And we know that since heat is released, the sign for delta E has to be negative. Remember that the system lost heat. And the only way that you can get a negative value for a delta E is if the final energy is smaller numerically than the initial energy. We can draw a similar kind of graph for the reaction of MgCl2 decomposing to make magnesium and chlorine. This reaction won't happen on its own. Magnesium chloride is fairly stable. If you want to make it decompose, you have to put energy into it, which means that your starting material, the MgCl2, has a fairly low energy, and your final products, Mg and Cl2, must have a higher energy. And that gives you a positive value for your delta E, which again fits in with our sign conventions that say a gain in energy must be a positive value. Those of you that are paying attention may have said, okay, this is all great, but how do we actually get EF and EI? We just talked about how complicated it is to actually calculate an internal energy because of the complexity of all of these systems. So if we want to change an internal energy, how do we actually find EF and EI in order to calculate the delta E? Well, it turns out you don't have to. The trick is, the change in internal energy, while it does equal EF minus EI, it also equals the sum of the heat transferred and the work done. And the important part about this is that heat and work are things that we can measure, either directly or indirectly. And remember that energy is a state function, so some processes will involve the change in energy happening entirely due to heat transfer and no work is done. Some will happen entirely due to work being done on or by the system with no heat transfer, and some will involve some combination of both. I'm going to give you those three different examples now, where the process involves a change from an initial energy conditions to a new final energy condition. So you can see that three different types of energy transfer are possible. Heat only, heat and work work only. And all three possibilities can give you a delta E of the same magnitude. A couple of examples that are commonly given in textbooks are a heat-only process will be something like completely draining a battery by using it to heat up a resistor. And an example where work and heat contribute to the complete draining of a battery, that might be resistive heating and work done by causing a fan to rotate.